So what we're going to go over today are some of the properties that ionic compounds show and molecular compounds show, what kind of properties some specific compounds show, because next week on Tuesday, we're going to be doing our first lab. In our first lab, you are going to receive about a dozen unknown compounds. They'll just be labeled like A through K, all right? What you're going to have to do is, using only the physical properties of those compounds, identify them. Right now, that probably seems like kind of a daunting task because we don't know very much about the properties of ionic and molecular compounds. But after today, we will know quite a bit more. And given an unknown compound, we should be able to make a pretty good, or have a pretty good idea of what compound that probably is based on its physical properties. So we're going to review physical and chemical properties from Science 9. Okay, we're going to talk about acids and bases. It's like grade 5 science. Okay, and then a little bit of stuff about ionic versus molecular. Okay, and some specific compounds in general. Okay, so understand how those properties can be used to identify a compound. That is going to be crucial. You're probably going to want to highlight a few things or make a couple notes about those. I'll drop kind of big hints as we go along here. Okay, letting you know this is going to be something that's going to be very useful on your lab. Okay, to help you identify this compound, right, or things like that. So just make sure you're kind of paying attention for those, because if you miss them, man, identifying those things on your lab report is going to be a lot more difficult. All right, so first off, chemical versus physical properties. Okay, we already know that everything, all matter is made of atoms, but it's the combination of those atoms, okay, that gives things their physical properties and their chemical properties. So chemical properties are things like reactivity, right? Whether this thing reacts with that thing when they're put in close proximity with each other, or whether this thing is totally inert, which means it reacts with absolutely nothing, right? That's a chemical property. Physical properties are quite a bit more numerous. Things like color, density, melting point, whether they conduct electricity or not, whether they're attracted to a magnet or not. Okay, all kinds of different things are considered to be physical properties. Right? Solubility, whether they dissolve in water, all of that stuff are all considered to be physical properties. Right? And we can use those properties to distinguish between ionic and molecular compounds. Right? It's important for us to be able to do that fairly easily, because then at least we're breaking up our unknowns into at least two groups. Right? I know these ones are molecular, I know these ones are ionic, and then it's easier to kind of break them down from there. Right? So we're going to look specifically at some of those kind of physical properties. All right, now here's some things we need to know about ionic compounds. Ionic compounds typically, and when I mean typically, I mean like 99% of them, exist as crystalline solids at room temperature. Right? Salt is an example of an ionic compound, and we all know what salt looks like. It's a white crystalline solid. All ionic compounds are crystalline solids at room temperature. Okay? Does that mean they all look like salt? No. Okay? Their shape of their crystals, the size of their crystals, even the color of their crystals is based on what are they made up of. Right, so we'll talk a little bit about that, because some of the metals actually create salts, that is the crystals, with specific colors. Okay. Now, another thing here, guys, with salt, the term salt, okay, we use that always to apply to this one compound. We say this stuff is salt, okay, sodium chloride. Well, specifically, it's table salt. Salts are ionic compounds in general. Anything that's an ionic compound is technically a salt, and you wouldn't want to put all of them on your food. Okay, there are lots of ionic compounds that are salts that would A, not taste good, and B, kill you. Right, so they don't all belong on food. Okay, this stuff specifically, okay, is table salt, sodium chloride. That's why we never use the term salt in a reaction. We go, well, I added salt to this. What salt did you add to that? It's kind of a general category, you know, including thousands of different compounds. Okay. They also have very high melting points. Okay, so ionic compounds have very high melting points in the several hundreds of degrees before they will melt into a liquid. Okay, the big thing about ionic compounds is, and we talked about this the second day, when you put an ionic compound into water, it does something called dissociation. That means the non-metal and the metal separate. right? We said that an ionic bond wasn't very strong because they both kind of got what they wanted. They got the electron or got rid of the electron they wanted to get rid of. Okay, there wasn't a lot of reason for them to stay together. So when they go into water, they split. And now you have these charged particles floating around in the water. Some of them are negative and some of them are positive. Okay, that allows their solutions to conduct electricity.
Can't you remake salt water by just heating the bottom?
Pardon me?
Like, can't you remerge it though? Because like in salt water.
Oh yeah, if you evaporate all the water off, they'll recrystallize, yes. But when they're in solution, that is, they're dissolved, they dissociate. Okay, and that's what allows them to conduct electricity. If I have pure distilled water, it doesn't conduct electricity because there's nothing dissolved in it. So there are no positive and negative particles in there to carry the charges, right? I mean, if you have a battery or a circuit, okay, you have to have a positive and a negative end in order for the electrons to flow, right? A molecular compound, and water is an example of a molecular compound, will not conduct electricity because it doesn't split into positives and negatives. Everybody follow on that? Okay, so ionic compounds will conduct electricity when they are in solution. And in fact, that is the one property, okay, that always tells you if something is ionic or molecular. That's going to be really important for the lab next week. Okay, a conductivity test. Okay, we call it the aqueous conductivity test because it tests the solution. Okay, if it reads as positive, you are dealing definitely with an ionic compound. Okay, the reason that that's an important test is there are some molecular compounds that are crystalline solids. Not many, but some. Sugar is an example. Okay, when you put sugar and salt side by side, they're kind of hard to tell apart. They're both white crystalline solids with small crystals. And if you put them in water, they both dissolve. The difference is the sugar water will not conduct electricity. Okay? Because sugar is a molecular compound. It's this. Okay? C6H12O6, that's glucose. Okay? It's a molecular compound, and when you put it in water, it does not split into positive and negative parts. So as a result, the solution doesn't conduct electricity. Right? You put salt in water, it splits into Na plus, Cl minus, conducts electricity just fine. Okay? Everybody with me on that? Okay. Okay, so ionic compounds, crystalline solids. Okay, so if you're like making a quick summary of this slide, ionic compounds are typically crystalline solids, high melting points, solutions conduct electricity. Okay, those are kind of the three big points for those. Now, looking at these pictures here, okay, we also see that some of the ionic compounds may have very bright colors, right? Anything that contains nickel is going to be green. Okay, so all nickel-containing ionic compounds will be green in color. Okay, nickel just always produces green salts. Okay, so nickel compounds, like we said, are green. All copper-containing compounds are blue. And all cobalt-containing compounds are red to pink, depending on what they're with. Okay, but they're typically going to have a reddish-pink color to them. Okay, is that going to be important if you're identifying unknowns and you look at something and it is a green crystalline solid? You have a pretty good idea what's in it. Yeah, okay, pretty good idea. Now, when I give you those unknowns, I'm also going to give you a list of their possible identities, right? So there'll be one green one. It's probably whichever one of those unknowns has nickel in it. Okay, so things like that are going to be important for being able to identify some kind of right off the bat. Okay, will we want to confirm that? Yes, we'll still want to dissolve it in water. We'll still want to check and see that it conducts electricity just to make sure that we're right. But chances are, if it's green, it's got nickel in it. If it's blue, it's got copper in it. If it's pink or red, it's got cobalt in it. Okay, we can always double check. Okay. Now, for molecular compounds, okay, molecular compounds can be any state at room temperature. Some are liquids, some are gases, and some are solids. Okay, but they typically have much lower melting points and boiling points. All right, water is a good example. It is a liquid at room temperature. Okay, it has a low melting point, 0 degrees Celsius. Okay? It also has a fairly low boiling point at 100 degrees Celsius. Okay? Right? Butter would be another example of a molecular compound. It's a solid at room temperature, but you only have to get it up to about 30 degrees, 32 degrees, and it starts to what? It starts to melt. Butter is easy to melt. Okay, it's a molecular compound with a low melting point. Okay, it's also not crystalline. Okay, butter, when it's a solid, is like oily and soft. Okay, whereas salt is hard and crystalline. Okay, does that sort of make sense? Okay? And you'll actually notice if you look at like sugar crystals versus salt crystals, sugar crystals tend to be softer and rounder, okay, than salt crystals do. Okay? It's a molecular compound. All right, so first off, so we said low, they can be any state. Carbon dioxide, that's another molecular compound. Okay? And carbon dioxide is a gas at room temperature. Right? So we've got lots of things here. They could be any state. Molecular compounds are not usually as soluble as ionic compounds, not usually. Okay? Sugar would be an exception. Sugar is quite soluble in water. Okay? You can dissolve quite a bit of it. But not all things are that way. You can't dissolve butter in water. Okay? Can't put oil in water, it won't dissolve. Okay? Things like that. Those are molecular compounds. They're not typically soluble in water. Okay? And even if you do get them to dissolve, okay, the solutions they form will not conduct electricity because, again, they don't break up into ions. They don't have ions. So there's not going to be any positive and negative particles floating around. Okay, so like I said here, in an ionic compound, you're going to have this kind of arrangement. This is also typically why ionic compounds are crystalline, because they are arranged uniformly, which lends to a crystalline shape. Whereas typically molecular compounds do not align uniformly, and as a result, they're quite soft or non-crystalline, okay, in their shape. There are exceptions. Obviously, sugar is an exception, and water is an exception as well. Okay? When water turns to a solid, it's crystalline. But are its crystals always the same shape? No two snowflakes are alike. Okay, those are the crystals of water, right? It very rarely forms two things that are exactly the same. All right, questions on the properties for molecular compounds? Now, molecular compounds that are soluble in water will produce clear solutions. Okay, there are basically going to be no colored molecular compounds, okay, that would produce a colored solution when soluble. Right? Think about it, you put sugar in water, okay, it's just clear. Alcohol in water, it's just clear. Okay? And alcohol does dissolve in water, by the way. Okay? You guys probably don't know that because you're not old enough to get alcohol, but okay, just so you know, alcohol does dissolve in water. Okay? It is soluble. Oh no, I didn't say it would turn clear. The stuff that makes alcohol colored is the other kind of impurities that give it its taste. If we're talking about like liquor, alcohols. No, if they're soluble, like the things that make, like, let's say a liquor like whiskey or rum or something a certain color, those are the impurities, not the alcohol. Okay, because it's not pure alcohol. Pure alcohol is clear. It is very clear. Okay, it is, yeah, and it is highly soluble in water. You dump it in, it just disappears. Okay. Yeah. Right, but yes, you're right. If I poured whiskey into water, the water would assume the color of the whiskey. It would be brownish, right? It would be diluted, but it would be colored. But that's not because the alcohol is colored. It's because the other impurities that make it taste the way it does are also in there. Okay. All right, does that sort of make sense? No, that's a little clearer. Okay. And I didn't mean that as a pun, a little clearer, but it's clear, right? Okay. That's terrible, I know. It was totally unintentional. Okay. Now, acids versus bases. Okay, we definitely are going to have some compounds in our lab that are strongly acidic and some that are strongly basic. That means lab safety. Don't taste any of them. Okay, there's no taste tests allowed in the lab. Okay, because for some of the things, if you taste them, it'll be the last thing you taste. And it won't taste good. It'll taste like burning. Okay? And yeah, that's bad, right? We don't want that. All right. So if something is an acid, it has a low pH. Okay, that is a pH less than neutral, so less than 7 are for all acids. Your strongest acids are going to be ionic compounds. Okay? And all ionic acids contain hydrogen as the metal. Okay? This is what makes things acidic, is that they have a hydrogen ion in them, okay, that will split and enter the solution, making it acidic. Okay? Because they're also ionic compounds and they dissociate easily, what are they going to do with electricity very well? They're going to conduct it. These will be your best conductors because they most easily split into positive and negative. Okay? Your acids and bases will conduct electricity incredibly well. Right? So hydrogen, okay, is going to be in all of our acids. Here's a very common acid. No, that's citric acid. That's different. This is hydrochloric acid. It's the stuff that's in your stomach. Okay? Helps you digest your food. If you have acid reflux, you feel the acid burning your esophagus. Okay? That's heartburn. Okay? It is actually burning. It is literally a burn. Okay, the acid comes up into your esophagus, which is not protected against the acid, and you feel it. If you vomit, you kind of get that burning sensation. That's your stomach acid actually giving you a chemical burn in the unprotected parts of your digestive tract. Okay, your stomach is protected by a layer of mucus that it constantly produces in order to protect the inside of the stomach. So yes, there's a whole bunch of snot lining your stomach, protecting it from the acids that are in there. If you have like certain problems with your stomach, you may get an ulcer. Okay? How many people have heard of an ulcer before? Okay? So an ulcer is essentially a chemical burn on the inside of your stomach. It means that you're not secreting the mucus enough, and some of the tissue of your stomach is exposed to the acid, and then it literally tries to digest itself. Okay, and so we don't want that. They can be quite painful and problematic. So yeah, you got to kind of avoid that. Right? No, you'd know. If you had an ulcer, you'd know. Yeah, like you get a lot. There's a lot of pain, a lot of burning, and sometimes vomiting and other digestive issues that go along with it. Yeah. Okay. Sometimes like even blood in your stool, it can show up if you have an ulcer. Bad. You don't want that. Okay. All right. So this is an example of an acid. Okay. Here's another example of an acid. Which one of those acids would be stronger? Yeah. H2SO4 would be stronger because it can give off twice as many of the ion that makes acids acidic. Okay? It has twice as many of them. Right? Similarly, this stuff's really acidic. Nitric acid. Okay? Really, really acidic. In fact, with most acids, you don't want to even get the fumes near you because they can be very harmful. Right? Back when I first started teaching, I was actually mixing some of this for a lab one time, and I had a cold, and I had the container open, and I sneezed right over top of the container. And what do you do right after you sneeze? You inhale sharply. So I inhaled all these fumes from the acid, knocked me out. Okay? I like lost consciousness, fell down, and one of my colleagues came in luckily a few minutes later, and I'm lying on the floor, blood streaming down my face like this, like he thought I was dead. Okay? Like, okay, unconscious, blood coming out of me. It was gross. Okay. Well, they weren't there. It was after school. I was getting the lab ready for the next day. So luckily, somebody found me. Yeah, but that stuff, obviously, the fumes can be harmful. Nitric acid's even worse. Okay? When I was in high school, we were doing a lab and we were using it for some reason. We never use it now. But when the container got left open on one of the desks, and two of the guys on the volleyball team, one of whom was the setter, okay, were doing their lab, and they had their hands over top of the container. Well, a few hours later, they started getting these blisters, painful blisters all over their hands because their skin had absorbed the fumes of the acid, and they got chemical burns. Yeah, so the volleyball team was without their setter and main middle blocker for like 3 weeks because they had their hands all wrapped and because they got these severe chemical burns on their hands. Right, so acids can do a lot of damage to tissue if they're very concentrated. If they're very dilute, they're not all that harmful. Okay? For example, this is an acid as well. It's just not typically a strong acid. No, sorry, no, that's not it. What am I saying here? That's ethanol, sorry. Okay, This is an acid as well, CH3COOH. It's acetic acid. We typically call that vinegar. Okay. The vinegar you buy at the store is very diluted. It's only 5%. Okay, so it's 95% water, 5% acetic acid. We have acetic acid in the lab that's glacial. It means it's basically the opposite. It's 95% acetic acid and 5% water. You drip that on the table and it eats a hole in it. Okay. It smells like vinegar. I ain't going to taste it because if it can eat a hole in the table, it'll eat a hole in my tongue. Okay. I don't really want that. Okay. It smells like vinegar, just really strong. In fact, most acids smell kind of like vinegar. They all have a very similar smell. You don't want to sniff it. Okay. If you sniff vinegar, you'll feel it burning in your nose, but it won't hurt you. Okay. You sniff the glacial acetic acid and you'll be flat on your back bleeding. Okay. You don't want to do that. All right. Now, other things about acids, like we said, they're all the strong acids are going to be ionic compounds, and they're going to conduct electricity. Hydrogen's going to be acting as the metal. Okay, they're crystalline solids at room temperature. We can't buy them as crystalline solids, however, because they're very dangerous in their solid form. We can only get them pre-mixed in water in solution already. Okay, they're highly soluble in water. If you were actually to have the solid, okay, it would dissolve very easily, very quickly in water. Again, the problem with that is when you put them in water, it's an exothermic reaction. It gets really, really hot, okay, really fast. It can actually shatter glass because it heats the glass up too much. Okay, acids taste sour or tart. We already said this is not a valid test in the lab. Yes, they're going to taste sour or tart, like a lemon or a lime, okay, or something like that. Okay, sour or tart. But they are going to turn litmus indicators to acidic colors. Generally, that's red, okay, in color for anything that's acidic. All right, and they have a low pH, less than 7. So some of the tests that we're going to run in this lab next week are going to be things like a pH test. Right, that'll tell us which things are around neutral and which things are acidic or basic. It'll also tell us. Some of the other tests we'll run, a conductivity test. That'll tell us which things are ionic and which are molecular. Okay? And we'll also run just some regular, like kind of observable properties tests. What does it look like? Is it crystalline or non-crystalline? Right? Is it like solid, liquid, or gas? Okay, things like that. It's kind of the easily observable properties will also be things we'll record because they'll help us to identify things. Questions on acids? Okay, so remember, this is the key thing here. All acids, strong acids, have H plus in them. So if on your list of unknowns, you have this compound, you know that this is an ionic compound, hydrogen's acting as the metal, and it's going to be acidic. All right, so when you're doing your tests, if you get one thing that dissolves really easily, is a high conductor of electricity, and is a pH of 2, it's probably that, right? So that's kind of the process that we'll go through when we're getting our data. These are the observations I made for this compound. What does it fit with? That thing I know should be acidic and ionic and blah, blah, blah. Okay, bases. Obviously, bases are the opposite of acids. They have a very high pH, but believe it or not, they're just as harmful as an acid. You can get just as severe a chemical burn from a strong base as you can from a strong acid, right? But for some reason, there's this idea that bases aren't as bad. They're every bit as bad if they're just as strong, right? The stuff we talked about the other day, this stuff here, sodium hydroxide is a very strong base. It's what we use in oven cleaner, right? It is so corrosive that it'll dissolve the burnt-on crud off the inside of your oven, okay? Bleach is an acid, actually. Yes. No, bleach is an acid. Chlorine bleach is an acid. Yeah. Okay. So ammonia, the stuff you use on windows, is a base. Okay, so sodium hydroxide is a base. All bases are going to contain hydroxide as the non-metal. All strong bases, that is, are going to contain hydroxide as the non-metal. So the more hydroxide they can give off, the more basic they will be. Same as with acids with the hydrogen. Okay, so they're ionic compounds because obviously hydroxide is a polyatomic ion, so they're going to dissolve easily in water. They're going to conduct electricity, okay, but they're going to have a pH that's very high. So, definitely above 7, probably more like 12 to 14. Okay. Typically, bases taste bitter, but again, we're not tasting anything. Okay, but typically, bases are bitter. Soap is a base. Okay, it contains lye, which is a strong base. Okay, and that tastes obviously very bitter. Baking soda is a base, tastes bitter. Okay, things like that. Okay, and typically they turn your indicators to basic colors, blue to black. Okay, really, really basic things tend to turn the litmus paper beyond blue, straight to black. Okay. All right. Questions with the properties of bases? Everybody okay with those? All right. So what we need to talk about now is what do we have to do with these things when we get to our lab. So on Monday, we're going to be sitting down and starting to design the procedure for this lab. Obviously, some of the tests we want to run are going to be things that can tell us which things are molecular, which things are ionic, which things are acidic, which things are basic. All right, so I want you to write this down, but this is the list of tests that we're going to have to run at some point during that lab. Okay, the first test we just call an observable properties test. These are anything that you can sort of see or smell, okay, or otherwise observe without doing anything else about a compound, okay, without having to test it in any other way, basically just to have it in front of you and be able to observe it. Okay. So from observable properties, we should be able to observe some things like color. Okay, and that's where we could figure out some of the ionic compounds, right? If it's green, it's going to have nickel in it. If it's blue, it's going to have copper, and so on. Okay, so color is going to be an important one. State. Solid, liquid, or gas. There aren't any gases. It's really hard to contain them. They tend to just float away. So there won't be any gases to test. Okay, but solid or liquid, obviously. And then the nature of that matter. Okay, and by nature I mean, is it crystalline? Okay, or waxy, or okay, kind of what's the nature of it if it's a solid, or what's the nature of it if it's a liquid? Is it a thick liquid? Is it a thin liquid? Okay, things like that. So like viscosity, I guess we would say would be what we'd be looking at there. All right. What else could you test just kind of having the material in front of you? Well, that would involve putting something else in it without having to kind of put anything else or touch it or anything like that. Okay. If I had a beaker of water and a beaker of alcohol, how would I tell the difference? Without tasting it. Smell. Yeah, alcohol has an odor and water doesn't. Okay, odor is an observable property. Okay, I mean it's possible, right? You could get two liquids as unknown samples in there, right? And I mean, if one of them's water and one of them's something else, odor might be the thing that allows you to tell them apart. They're obviously both molecular. Okay, so they're both going to have a lot of the same results. Okay, maybe the only way you can tell them apart is that one is stinky and the other is not. Right? So odor would certainly be something we would want to observe there. Those are probably our top ones, top things that we would want to observe about all of the unknown compounds, okay, and kind of record in a chart. Okay, so that would be one of the tests, observable properties. Okay, if I want to test the conductivity, what do I have to do to the stuff first? Because I'm not testing the conductivity of the material. I'm testing the conductivity of its solution. Right. I got to dissolve it first. So when I do that, that's essentially testing whether it is soluble or not. Okay? It's a solubility test, testing how well or if at all it dissolves in water. Okay? we said ionic compounds typically dissolve very well. Molecular compounds, not always. Does that mean there are some? Yes, some that do, okay, but most don't. So if I've got a bunch of compounds and I test all their solubility, any ones that don't dissolve are not ionic, most likely. Okay. Another thing I would check during the solubility test would be for any color changes. Okay. Sometimes things would change the color of the solution. Okay. I mean, typically if I put red crystals into water, the solution will probably assume the color of the crystals and be red. And another thing to watch for would be temperature changes. Okay. You will have a couple of compounds in that lab that will cause temperature changes. Okay. Typically things that are strong acids or strong bases, when they dissolve, will increase the temperature of the water. Okay. And there's also going to be another unknown, and it's this stuff. Okay. Ammonium nitrate. How many people have ever used one of those instant cold packs where you pop the little water bladder and shake it up and it gets cold? Okay, the powdery stuff that you can hear shaking in there is ammonium nitrate. When it dissolves in water, it gets colder. And it's one of the very few ionic compounds that does that actually gets colder when dissolved. Okay, so it'd be one to watch out for because it's one of your unknowns in the lab. All right, once I've done the solubility test, now I have a whole bunch of solutions. Now I can test the conductivity of the solution. So I would say that's probably the next thing that we would want to test. Right? We've got little conductivity apparatus. Okay, you just push the button on it and stick it in the solution, and it'll give you a reading between 0 and 10 for its conductivity. Basically, anything between, let's say, 6 and 10 is a pretty decent conductor. Okay, anything below 4 is a very poor conductor. There are not going to be very many compounds that are not either really good or really bad. Okay, you're basically not going to get any 5s. Okay, if you got a 5, something went really wrong. Like you forgot to rinse it off, okay, after the last test or something like that. Okay, so conductivity, okay, just going to be a number between 1 and 10, okay, listing how well. Okay, remember that ionic compounds conduct. Okay, molecular compounds do not. All right, the test I probably want to run last is pH. The reason I want to run the pH test last is because it will chemically alter the material. Okay? It's a chemical reaction with the pH paper that causes the color of the pH paper to change. Right? So once I've run that test, I no longer have a pure sample of what I started with. So I want to do it last. Okay? pH is just tested with paper. Okay? We have the Hydrion paper that shows all the pHs between 1 and 13. 14 is kind of on there, but it's hard to tell the difference between black and blacker, okay, on there. So it's just got a color scale on there. You just compare your sample to the color chart in the bottle, okay, and then you're done. Okay, those will be the tests that we'll have to run. Once we've run those tests, we should be able to identify what each of the unknowns are. Okay, like we said, right off the bat, we should be able to pick out a few because of their colors. Right? Sometimes odors will give them away. Okay, there'll be a couple that'll have kind of strong, distinctive odors. Okay, that'll help us to identify them as well. Jason. Yep. All right. Questions on how that's going to work? Okay, so like I said, on Monday we'll have the Chromebooks, and I'll kind of show you how the lab report's going to set up, and we'll get started on the hypothesis, the variables, and designing the procedure. Okay, making up an observations chart to use when we're in the lab, and all of that kind of stuff. Now, with regards to being in the lab, I do not tolerate any horseplay in the lab. Okay, if you're fooling around in the lab, you're a danger to everybody else, and I will kick you out. No warnings. Okay, I see you doing it, you're done. I don't take chances with people's safety in the lab. So please keep that in mind. The lab is not a place to fool around, be pushing, shoving, doing whatever. Okay, there's no tolerance for that. Other safety things. When we first get in there, you will have the option to put on a lab apron. I don't make it mandatory. You can wear them if you want, but it's probably a good idea. Okay. The one thing that is not optional is eye protection. Okay. There's goggles in the drawers of every single lab station. Once you get in there, you put them on. We don't take them off until I say it's time to go back across the hall. Even if you're done your lab, there's probably somebody else who isn't, and you'd be surprised how far things can travel, okay, in the lab. So we keep the goggles on until everybody is done. That's something you'll get one warning on. Okay, if your goggles are not over your eyes, you'll get one warning. After that, you're out of the lab. Okay, I'm not going to take any chances with you being blinded. Right? If you wear prescription glasses, you have to wear the goggles over top. Okay? Prescription glasses do not provide protection from the sides. Okay? So we need to make sure that we are protected from the sides. So we have, if you have prescription glasses, we've got big ones that'll fit over top, big goggles that'll fit over top. Okay? If you would prefer to wear contacts on lab day, so you can just wear the normal, somewhat more stylish glasses, okay, that's obviously an option as well. Okay, but you do have to wear the goggles all the time because it is no fun when somebody gets something in their eye. Okay, because I've had to put somebody in the eye wash station and it did not end well for either of us. Okay, well, because they got something very acidic in their eye and they were screaming and flailing and running all over the place. And when I grabbed them, they flailed and smacked me in the face and I started bleeding. And then I got angry and I grabbed their hair and took them over to the lab, to the eye wash station and jammed their head in and I hit their nose on the bar that goes across. So we're both sitting there bleeding and it just wasn't good. Yeah. So I try and avoid that if at all possible. Blood is bad. It's supposed to stay in you. Yeah. So just wear the goggles all the time because, yeah, that was just like traumatic for everybody. Okay. So make sure you're always wearing the goggles. Like I say, I'll only ask you once on the goggles. Other lab safety things for the lab, footwear. Okay, I mean, this time of year, it's not usually too big of an issue, but you do need to have shoes that cover your foot. Okay, you can't wear open-toed shoes or open-topped shoes like sandals or flip-flops or anything like that in the lab for a couple of reasons. If anything spills, it'll run off the counter and onto your bare feet, okay, or sock feet even, and that could cause a chemical burn. There's a lot of glassware in the lab, and we can't guarantee that there aren't, maybe tiny pieces of broken glass on the floor. And if you're not wearing proper footwear, you could cut your foot, okay, things like that. Or if somebody drops a piece of glassware and the glass flies over and hits your bare foot and cuts it, okay, we just don't want to take any chances with that. So you do need to wear proper footwear. If you have long hair, you need to put a hair tie in your science binder so that you always have one when we go to the lab so you can tie your hair back. Okay. Clothing, wear it first off. It's always good. Okay. But secondly, if you have drawstrings like on a hoodie, okay, those need to be tucked in or tied up so that when you lean forward, they don't get into the chemicals. Okay, because I've seen that happen as well. So anything that's like really loose, if you're wearing a jacket and it's not zipped up, or like I say, you got the drawstrings or something like that, you got to make sure that they're tucked away, or just take the hoodie, and leave it in the classroom or something like that. Okay, but you do have to make sure that none of that stuff can happen as well. That's why we have to tie the hair back. Okay, hair that gets into acid doesn't look as nice after. Okay, it's like hair that's burnt. It smells about the same too if you ever smell burnt hair, and it's a very distinctive smell. It's awful. Okay, so we want to avoid that if at all possible. All right. Beyond that, if you get any unknown compounds on your hands, okay, and that happens sometimes, that's not the end of the world. Just go and rinse under the sink, cold water for 5 minutes, and we'll check on you and make sure you're okay. But generally, you get it on your skin, it's not too big a deal. Your skin is pretty protective and pretty resilient. Okay, so just make sure you quickly rinse it. After the lab, always make sure you wash your hands, soap and water. Okay, well, you should do that anyway because you don't want to eat with dirty hands. But secondly, you never know if you got any chemicals on your hands, so make sure that you wash soap and water. There's soap, water, and paper towels at the sink on the way out of the lab, so everyone can use it. Okay. everyone should have a role. Yeah. Okay. In the lab, when you have your group, and I'll let you choose your group members. Okay. But everyone in the group should have a job. Okay, the worst thing is when there's somebody who's kind of just freeloading off everybody else or getting in the way because they don't have something to do. Okay, make sure everybody's got something to do. You're the guy who does this measurement or the girl that does this measurement or whatever. Okay, but just make sure everybody's got some job that they can contribute to the lab. Okay, otherwise the people that are not occupied tend to be the ones causing problems. Okay, so make sure everyone in your group's got something to do and follow the procedure carefully. If you don't, your data will not be good, and then you will not be able to identify the compounds properly. Okay, and that's probably the number one reason for people to do poorly on a lab report is they just get bad data because they weren't careful enough. Okay, so you want to be careful, you want to get good data. Okay, and you can always compare your data to mine. Okay, every time we do a lab, I'll also post a video of me doing the lab. Okay, so you can double check your data against my results. Okay, and that's always a good idea. It doesn't take very long, okay, but it's always a good idea to double check against the data that I got. Okay. All right, other stuff for the lab. Oh, we don't take the Chromebooks into the lab. Okay, we'll have them that day, but we don't take them in there because obviously we don't want anything to happen to them. Okay, anything gets spilled on them. So you will need a paper copy of your observations chart for that day. Okay, so we'll make that the day before, and then you can print one at home or make one by hand or whatever. Okay, but we don't take the computers across the hall. If you want to take your phone across the hall, that's fine. And if you want to take pictures of what you're doing as you're doing it, that's also fine. In fact, it's probably not a bad idea. Okay, I've had lots of people who actually video what they're doing so that they can go back and confirm their results afterwards. Go, okay, so when I put that in there, this is what happened. Okay, and they can go back and double check. Not a bad idea. Okay, you have the technology, you might as well use it. Okay? Plus, you'll have my observations video as well. Okay, so we'll do that lab on Tuesday. Okay, and that'll be kind of the last. We'll have Monday to work on the kind of pre-lab stuff. Tuesday we'll do the lab, and then the lab will probably be due like the following Monday. Right? So you'll have lots of time to work on it, and then come in and ask me for help if you need it, okay, and get all those questions answered. If you want me to look it over, okay, that's when you need to do it, right? But you'll have a fair amount of time to do all that. Just don't leave it till the last minute. Okay? If you leave it till Sunday night, that's when the power will go out or your computer will die or something like that. Calamity knows when you're not prepared for it, okay? And that's always when it happens. All right, any other questions to do with the lab or with properties of compounds? Okay, so this lesson you'll definitely want to refer back to in your notes when you're trying to identify your unknown compounds, okay? Because all the information to help you do that is in this lesson. Okay, for the rest of class, I want you to finish up the naming worksheets, okay? For the work on the toughest ones. I'll put them back up on the board, okay? But I want you to work on the toughest ones because today's quiz was actually pretty easy. Okay, I didn't give you too many tough ones on there. Okay, there are definitely tougher questions than the ones I gave you today.